Okay, so we're going to cover as much as possible of the sort of state of the arts of deep learning in the next 4 lectures. And I should thank Adam Brendel for allowing me to use some souped up version of his content for this course. So Adam gave a nice deep learning workshop, a full day workshop in Dublin at the Spark Summit that I attended. And so, I'm trying to learn deep learning, and it's used heavily in a lot of the industries, and there's a lot of hype about it. But it's also the tools behind Google's, machine translations and object recognition, and it's solving a lot of problems. And the more sophisticated variants of it include algorithms in self-driving cars all the way, right? So we should put it into our toolkit somehow. So here is the plan. This is just a slight mathematical aberration of what was done in the Spark Summit. Okay, so this is actually something I played with. So I took deep learning from Udacity. I don't have time to complete it, but so you can do this kind of transfer learning and do some interesting art with it. So you can check out this paper, Mona Lisa. So yeah, you should be able to, if you get through all the content, which is the plan here, you should be able to do those kinds of paintings of yourself. I don't know if it's worth it. And you can go all out and have 3D scans and then do 3D images and print and become an artist too. So what we will do is give an introduction to the area, sort of slightly historical, and then we will get into the basics of TensorFlow, which is Google's open source version for doing lots of things, not just deep learning, where the primitives are essentially how tensors are flowing through directed graphs, right? It's very general, and tensor is nothing but a generalization of a matrix, right? So it's just structured numbers flowing through networks. It's a very general formulation. And that's the technology we need for deep learning as well. Okay, so deep learning is nothing but essentially a particular class of artificial neural networks, and you will see what is deep about it by actually doing a little U-try in the end today. And what we will mainly be doing is so-called feed-forward networks. Once again, you'll see concretely what it means. It's feeding forward because there are sort of layers, and it's taking some input, and then it's feeding that input forward to get an output, right? And a lot of the language comes from, I guess, what is it called? Neurology, neurobehavior, like that, studying how animals' neurons work, at least initially, right? Then, of course, we have to train the neural networks to solve the decision problem at hand. It could be prediction or classification, regression, whatever. Today, we won't be able to. We will get next into convolutional neural networks, which were still kind of very popular. You'll see what they are. They're extremely good for images. And then we will get into recurrent neural networks, hopefully, and long short-term memory ones as well. The rest, I am not sure if we will have the time to go to it, but ideally, I would like you to understand how to at least use a generative neural network, and at least have a little idea of how to play with reinforcement networks. So this is when you start training a machine to learn from playing games. So this is very popular, right? The paradigm of learning. In fact, there was a whole theory course on reinforcement learning that I couldn't go to because of you guys. but so at least it'll get your hands dirty, and there's quite a lot of industry current technologies right here, right? So this is Adam. He's quite sharp looking in the picture. He did a pretty amazing job of doing all this in one day, right? Oh, by the way, so this is the plan for spring. Um, so so I kind of got inspired from Adam's workshop to do this 360 in 525 minutes, right? Well, the guys in the industry can do it. I mean, we should be able to. You guys are much younger, right? So I thought, hey, we'll do this 360 in 525 minutes. And in some sense, this is really motivated or informed heavily by you guys, right? Because I'm sort of back in the northern hemisphere after 10 years, so it's and like when I see you guys like getting confused about concepts like Lee, the stuff with her eyebrows, and so I kind of know what you guys don't know a little bit more. So I sort of reverse engineer stuff. So in particular, what I recommend you guys should have done before my course, this course is this one. So mathematical, statistical, and computational foundations for data scientists. So this won't be like measure theoretic, like hardcore graduate level probability in mathematical statistics. No. So this will really start from someone who's a good student in high school, pretty good with calculus and algebra and some programming, and then it'll very systematically construct everything properly, right? So you should be able to read the book by Murphy without any worries after the end of this, right? Kevin Murphy's book on a probabilistic, what is that? Probabilistic perspective of machine learning. Yeah, probabilistic. Yeah. You won't really have the training to read, say, Luke DeVroy's book on a probabilistic theory of pattern recognition, but if you're a pure math student and you've not done statistics or probability, then taking this course will help you go all the way, basically. And the main thing is I want to emphasize this lab lecture thing. So we will use LaTeX and a little bit of Blackboard. And but as soon as we learn a concept, we will also implement it in a sort of modern, computationally constructive way, right? So there won't be any, so everything you should also algorithmically understand. So this maybe is one thing. I guess Dimitri is going to maybe working in some big company by then. I have no idea, but let's see what happens. So I'm trying, because I'm sort of a domain expert in population genetics. That's kind of my thing. Although I don't do lab experiments, I work with biologists. So I'm going to do a module in that. This is my own research in mathematics. I'm in the math department, but this is really for PhD students in pure maths. You guys can skip it, the 0-1. And then, I don't know, depending on what you're after, right? So this is sort of social media and big data. So there's Professor Simon Lindgren. I think he's from Umeo. He's quite good. So he'll be, he's not a statistician either, right? So these guys are, I don't know, they're digital sociologists, right? So they're actually sort of doing like humanities. They're talking about what's going on and to their colleagues. And so this is important. Even if you want to be do statistical hypothesis testing, things like this, you need to know what hypothesis to test. You need to figure out what's going on, right? So he's going to give a one-day introduction to digital humanities, what the questions are, what are the data sets, what are people interested in from a humanities point of view. And then the second day, I will essentially have a slightly more formal take on what we can do about it, maybe doing our own designs. So it'll be similar to the Twitter stuff we did. I will maybe try to get into the G-Delt. This is the global news streams I told you guys about. And again, this is done with domain experts, geospatial analytics on big data. So this is Department of Social and Economic Geography. So these guys are quite interesting. So we have for example, they have data sets of cell phone trajectories of all of Scandinavia for several years and up to some coarse privatized resolution. So there's a lot one can learn from it. There's also real problems. about how to respond in case of some emergency. I don't know, Russians dropping bombs or terrorists going crazy. You know, it's a fundamental problem. You need to figure out from the historical trajectories of how peoples move, what you can anticipate that can happen on a particular location due to some whatever attack or whatever. Or say there's it is a security angle, right? But of course, there's other angles. You know, if you're an immigration agency, Sweden, you're interested in understanding, you know, segregation patterns based on economical, you know, earning potential or whatever, you know, all kinds of. So I shouldn't say, but they will tell you for a whole day about what they do, and also they will give you a hands-on lab on non-distributed geospatial analytics, which is kind of what most of them are doing. And then the second day, I'm talking to, you know, the authors of the book, Mastering Apache Spark for Data Science, that you've been reading, Mariama and Lee. So they are helping us set up the infrastructure we need for this. So you can take the same exact code and apply it to petabytes of trajectory data and geospatial data. So that's, I mean, this is cutting edge of, you know, what security agencies and Interpol can maybe not even do, right? I don't know. We don't know what they do. So anyway, that I highly recommend, no matter what you do, right? So even if you're an electrical guy, you still need to understand how to process spatiotemporal trajectories, right? How to integrate that with OpenStreetMaps, if it's roadways or whatever, right? So these are, and that's the whole point, because you need enough knowledge about fundamental domains, because whatever you're going to work on, usually you'll have to integrate information from different domains, right? And you have to learn from domain experts on all this. This one you guys can skip because this is basically a quick crash on data science in one day. So I'm modeling that after the workshop that I didn't take in the meetup in Dublin. Okay, so maybe that's enough advertisement for the course. Yeah, some logistics, you know, you have to bring your own water packs and cookies. I'm not going to be able to supply. I'll just make sure that wireless works and bring your laptop. I am on the lookout for Fika, you know, but 1,000 SEK per, you know, per day. Is that a lot to ask? I don't know. Yeah, I mean, you know, that's what it costs if you order coffee, right? And so we've been making coffee, but I don't have PAs that I can pay to make coffee anymore. So, so maybe that's not a good idea. But Tilo is going to bring Fika today. So anyway, we'll see how it goes. So, okay, let's get back to this. So yes, so Adam has quite a lot of experience building systems for startups and large enterprises. 10 years teaching both front-end and back-end technology, so it's a pretty unique guy that we can learn a lot from quite fast. Okay, so yeah, so he's worked in different industries, right? Finance, insurance, travel, media, entertainment, government. And I just like helping him a little bit with LaTeX, right? Because there is Lua LaTeX and KaTeX, and so he said with LaTeX not working in Databricks, so I'm going to fix it for him. That's what I've been doing. Okay, and I am also quite sure that in few months this will become outdated. Trust me, I have done hundreds of hours doing something like this last year in New Zealand. It's gone. There's so much happening. So you know, if you understand it, you understand it. And again, if you use it in a for-profit setting, you're supposed to ask Adam. Okay, here are our goals. So we want to understand deep learning, acquire an intuition and feeling for how and why and when it works, so you can use it. There is really no magic here. At the end of the day, there is just a lot of arithmetic operations, you know, addition, subtraction, multiplication, division, and you know, all these nonlinear transforms are just logical operations coupled with some finite series expansions of these trigonometric functions or exponential functions, right? So we're just doing arithmetic and logical operations at the end of the day, and we're limited by local optimization routines. So you know, those routines can always get stuck in a suboptimal, you know, place. And you know, but people have done a lot of beautiful art over the last few years to like make a lot of things work, right? It seems like magic, but so we will sort of learn from this. Yeah. And of course, this is taught in a way so that, anyone can do this. So you don't really need a PhD in mathematics. In fact, that was the whole point of a lot of this talks. Because if you're, if you see the what do you call it, the plenary talks in Spark Summit, has anyone seen it? Well, it's interesting. You should totally. I would see it if I were you, right? So one of them was very cool because it was a problem of recommending shoes, to users, right? And if you use the standard methods, it performs horribly, right? It doesn't look at the texture of the shoe, the color, the height, all of this. So what one of the plenary speakers, what she did was, and we might get into that here, is to basically download this Google's pre-trained model on lots and lots of images that I don't think Uppsala University has the resources to do this, right? Most universities don't, right? Because Google does this on its farms, or I don't know how many petabytes of data. But then they suck this model, train on all this, and then they just give it to you. Then you can basically download it and use it to essentially get features out of your data. So you may only have 20 James Bond cars or whatever you want to detect, or maybe 200 shoes, right? For a bunch of users. Then you can sort of feed those small data sets through this trained model and then get new features. And then, basically now when a new person come with a couple of shoes, you can just pump it through there and recommend shoes for them, basically, okay? So that's called transfer learning, right? So these kinds of things are expected to be done in industry by, anyone, literally. That's how they. So in some sense, a lot of this is this whole course has been like this, right? But so this is a data set that we've seen already, the MNIST data set, Mixed National Institute of Standards and Technology. And, we've done image recognition on this using, we did it with random forests, right? So we can do that with deep learning later. Yeah, I mean, this is the problem, right? So, children can easily detect with 100% accuracy, but it was very hard to do this on machines, and until recently, right? So you have sort of 99% accuracy only achieved in 1998 on the best ML systems. And of course, if you want a self-driving car or not, if you want a self-driving car, you cannot afford 99.99 accuracy. I mean, Andrew Nick talks about this, right? Yeah. And and if you want to make sure that your near-Earth asteroid mining robots that are going to land automatically on a many-body problem, you have to guarantee 100%, right? Because you could cause a near-Earth extinction event if you make a mistake. You know what I'm talking about? Because the asteroid could come and hit the whole planet. So, okay, so that's the angle, the mathematical statistical angle and the arithmetic angle some of us have is at that, But of course, for recommending shoes, who cares, right? It's like 1 out of 1,000 people are pissed off, like, oh well, what am I going to do? 1 out of 1,000 for a shoe recommendation, and they can just walk to the store and find shoes, right? All right, let's just go back to the course. So anyway, I just want you to understand that there are problems and different 99.997 point for different problems. All right. So here is basically, you guys know about this problem, right? We have a 28 by 28 pixel image. That's basically our input, and and so these are some language, right? So we have, this is in the grayscale. So we had 784 values, and 784 values are the indices. And then you can have 0 for black or 1 for white, or in the grayscale between 0 and 255. And depending on how a particular input dimension for the problem is, you can encode the inputs. and then the response is going to be numbers in this example between 0 and 9. So you've seen this before. So when these are discrete, you recall this is called a classification problem, and when these are continuous, it's called a regression problem, right? And the regression problem we saw was, say, the price of the diamonds, right, data set. So you have all these features about different diamonds, and then you're trying to predict its price. So we'll look at these basic classes of prediction tasks, classification or regression soon, using neural networks. Okay, so and we are going to be limiting mostly to supervised learning. So you guys remember what supervised learning is? So there's labels, at least for some of the data. Okay, we all know about training and test sets and prediction, and we've done validation, because remember, we have to make sure that we don't overfit. So we hold out some of the data and then do some kind of cross-validation. And this is the so-called principle of empirical risk minimization, say Vapnik. So yeah, so I think later on we're going to get into other losses like cross entropy. We'll come to these things later. Yeah, and often we've done this as well. We have to usually center the data and rescale it so that by dividing by the standard deviation in each dimension. Okay, so yeah, these are just Adam's notes. So here's some high-level things. So in decision trees, are good, especially if you want to interpret them. They usually give you some conditional statements, but they can be very hard to generalize. They will reach limits on different problems, because at the end of the day, you're just doing some kind of splits, right? You're doing axis parallel splits along the feature space. Okay, so in logistic regression, yeah, so I don't think we've seen logistic regression yet, right? So logistic regression is just like regression, except what you're trying to predict is, say, a binary thing, like spam or no spam. And instead of using like a linear, what's called activation or linear function in the end, you would use something called a logistic function, right? That essentially maps the real line to some kind of S-shaped curve between 0 and 1. And if it's above half, you say your prediction is 1, and it's below half, you say it's the same. And we will see that in more detail now. So yeah, these we haven't seen, but so if you've done machine learning course, know about support vector machines. So the general problem with a lot of these methods is they don't really scale in terms of the number of features. Okay, and when they do scale, they don't have enough complexity to fit the data well enough. Okay, so this is where deep learning comes in. So we are going to sort of explode on the parameter space, how many points we're using to fit our data, carefully. But the main magic happens because of this non-linearity that we add in and the layers we added, and you'll see this soon. Okay, so this is my mathematical statistical caveat I already blabbered about, and it's very important to to know what is the problem. Okay. So let's get our hands a bit dirty. So here is the artificial neural net, the oldest one, the original one. It's also called a perceptron. So how many of you have seen a perceptron before? Oh, God, everyone. Okay, these 3 people. So I will only move forward if Lee is happy. So Okay, basically what do we have here? We have inputs x1 through xn. They come in through this gray layer. This is the input layer. It's going from left to right. And then we have these weights, w1 through wn, sitting on the edges. So they're both real numbers. And this x0 is like a sort of a scale term. It's called the intercept. So we just fix that to be 1 for the perceptron. And then it also has a weight, unknown weight, w0. Right? So all we're doing is like multiplying these pairs of numbers, each of these pairs, x's with w's. And then in this node, we add them. Okay? So that's basically what's happening here. We just do wi times xi as I goes from 0 to n. Right? N or n plus 1 multiplications and n minus 1 additions. And then we go through this node. This is the, and then this function is called the activation function. So if this, whatever is coming in, is less than 0, we let it be 0. If it's more than 0, we let it be 1. So in the end, O, this little O is just what comes out of the output. The output is 1 if the dot product of w's and x's is positive, or it's 0. Otherwise, it's 0. Okay. So what is all this? This is really nothing but a hyperplane, right? So we basically, if you look at the space of x's, then all we are doing is, given these observed x's and some fixed weights, right? We are basically defining a hyperplane, okay, in the x space, such that if a new x comes in, okay, you just put the new x's here, put the fixed w's, and then see if the dot product is positive or not. If it's positive, then it lies on one side of this hyperplane defined by w's. Otherwise, it's on the other side. Okay, that's just all we're doing. And we'll complicate this concept. So usually this is called the input layer. This is one of the inner layers, and this is another one, and that's the output layer. And these are called nodes as well. So we have only one node in this hidden layer, and this is, yeah, you can think of it as another node with an activation function in this final layer. So formally, we have this. We have some function f that has the known x0 and a bunch of x1 through xn inputs. And remember, I put a semicolon here. This is classical math stats notation to separate the inputs from the parameters. And then these are parameters, right? W0. And all I'm getting is just this. I'm just rewriting this. Okay. And the implementation in terms of arithmetic and logical operations are the following. So we have n inputs from one n-dimensional data point. So Rn this is just the Euclidean real space, minus infinity to infinity, excluding points at infinity. And the power n means it's a Cartesian product. So in n is 2, it's a plane, n is 3, it's a three-dimensional space, and so on. And then arithmetic operations are just like this, n plus 1 multiplications and additions, some Boolean operations, and so on. So this is just notation. This means belongs to, so little o. This just means the output belongs to the set containing 0 and 1. So, in this 3-day, 3 Friday course, you will get comfortable with writing and reading notations like this. Okay, so we have n plus 1 parameters of interest, right? So, so this is the W0 through Wn. Okay, so I've already told this, and usually what you're doing is you're interested in finding the estimates of these parameters, so put a hat on them. So these are formally estimates, and so these estimates must be somehow statistically meaningful and justified. So, and these estimates are found using usually k-labeled points, right? So this is standard notation and to represent the k label points. So I usually put superscript parenthesis 1, superscript parenthesis 1, blah, blah, blah. This means it's the first example, is the machine learning lingo for it. So I have my label for the first training data and the features for the first training data. And usually these are rows of some training matrix, right? So it's just some notation. This is the kth one. And this is an element of what? It's an element of r to the power of n plus 1 cross 0, 1, right? Because I have k, this k is just the k training examples, and the features live in this space. I'm just fixing 1 to be constant, otherwise it will be, pretend 1 you don't know, and it makes the same sense. And then I'm purposely representing the output as a vector containing only one element. Everything generalizes all the way, pretty much, right? This formalism. So you know, if you have two outputs, then this can be a vector containing two elements. Okay, so this is basically the machine learning problem. And now let's just take kind of these formalisms. So what we're actually interested in is a random mapping. So we're now already like pure math stat decision theoretic problem. So this is actually formally called a Markov kernel. You know, it uses everything you know up to now and makes a decision. It's like hunting with a harpoon, basically. So it's a random mapping, and I'm kind of using this bad notation because I can't find the right thing for in this LaTeX. But so I'm just saying, so this is just Bourbaki's maps to, right? Bourbaki notation from France, right? It's Bourbaki's maps to. I'm just sort of perturbing it because it's a random mapping. It's a random mapping because I don't know what observations I'm going to see each time I repeat the experiment, right? So it's just science. So if somebody comes and repeats it, they may get a difference at a label point, right? Or you get some other people to supervise, find labels, they will do it slightly differently. So that's why it's random, but no matter what it is, as long as we have k of them, right? And this is label data, k of them, I must have a procedure, which is you know, the estimator, that will produce something that I'm going to call the model, right? And what does the model do? The model takes unlabeled data with some weights we found out magically somehow, and takes any data point in you know, with input data, and produces points in 0, 1. Right? This is just the formal way of seeing this. And there should be no ambiguities at all, because everything is in sync with the notation in Apache Spark, right? So we already saw that estimator, something we did, right? And then the estimator returns a model, right? Remember, these are exact same notions in Apache Spark. So I put up this sort of computer format font or whatever, right? And the model is a transformer, remember? The estimator returns a model which is a transformer.
And then you transform.
Yeah, exactly. Unlabeled data comes in and you apply it to the model, it transforms the unlabeled data to labels, right? So all of this is just completely consistent. So if someone tells you, I do machine learning, not statistics, or I do statistics, they just haven't read things in the last 20 years or so. I mean, I'm not saying in a mean way. Myself, I was just like this like 4 years ago, right? Because I come from a stats tradition. I'm like, oh, this is an estimator, blah, blah, blah. And then, but thankfully, like very famous people in Carnegie Mellon and Berkeley have like really clear textbooks and nomenclatures for this. So in fact, like all of statistics by Wasserman is an excellent textbook. You know, the second page basically has a glossary of this is what machine learning community means. But now the languages are gone. Like, you know, new people that are trained, even you saw in Apache Spark, mathematical objects are implemented, right, in the same way. So, all right, let's just focus on, and what I'm claiming is this. I'm actually claiming that this is the problem generally, right? The W's will change, the parameters will change, but the general problem is finding some kind of a random mapping from the data space to the, with the labels to the space of just labels for any arbitrary data. Okay, what is a linear perceptron? So, um, so the linear perceptron basically is going to let us bridge from traditional linear regression, which we did for the pipelines. Sorry, not what is it called? When you need to stay warm, the stuff. What did we do? There's temperature, atmospheric pressure, and then electricity. Remember this power plant, right? Because that was the power plant that took the extra load somewhere in. So anyway, so we're gonna now basically do perceptron. Think of perceptron as a linear regression problem, which it is, if you use the right activation function. So as I said, I'm not like a Scala fanatic. I just learned Scala recently, so Python's fine. And in this case, it makes no sense to write this in Scala because I'm just using Python pandas, right? So, and scikit-learn and so on. So let's just jump right in, and you guys should be able to evaluate this because all the libraries are already there in Community Edition. Okay, so I'm importing pandas and scikit-learn and so on, and I'm going to revisit the diamonds dataset in Python now. So let's display this and do some options. So I'm basically asking to see the 10 rows. So this is just our diamond dataset. Caret, cut, clarity, depth table, price, and then the X, Y, and Z relative sizes of the diamond. Okay, so and our goal is to predict the price based on the features. Okay, so the first thing we notice is, okay, we have like what do you call it? Categorical variables in the cut and color and clarity, right? Discrete categorical variables. So say I'm just first of all dropping the column 0 because that's just some indices, and then now I have what I want almost, and then there's this. You guys know this, or those who know Python pandas, you know the get dummies function. Well, this is what we call one-hot encoding in earlier, right? So we'll just see what it does. So I'm basically saying df3 is this get dummies of df2. So all it does is one-hot encoding, right? So it now takes the cut column and adds underscore ideal, and yeah, exactly. So now you see anything beginning with a cut should always have a 001 or a 010, or you see. So it's called one-hot encoding. So now we basically have moved from just moved to the number lines, right? So we've done these things before. It's just now we're going to pre-process to get y. So this is just the prices. So I'm basically taking the y's from the right place and flattening it, and now I have all the prices. Okay, and then if I essentially look at the columns I really want, and pre-process. So what I really need to do is drop the price that I took out, and I'm good to go, right? Turn that into a matrix, and this will report the shape of the matrix. So you can take each of these snippets, put them in a separate cell if you want to really understand pandas in a hurry. But
sorry,
yeah.
You took only 3 columns from df3, or what does?
No, I'm dropping the third column.
Dropping.
Yeah. Yeah, please, stop me. And it's a good check because I haven't done Python in a while, so but we can figure it out. So, I just looked at it and I added these comments for you guys just now because Adam just has no comments. I mean, to people who see Python all the time, this is like Python is talking to you, right? Anyway, so this is X train, X test, Y train, and Y test. I'm just, so train test split gives me, training data and keeps the test data. So here's so I'm doing a 25% split. I have a random state, some seed. I left all the seeds as an atom, and that's it. So this gives me my training and my splitting. And then he's running the decision tree regressor from scikit-learn. So that's what's going on. And so, max depth is how deep we go. That's given. And some initial random state is given. And you can, run this. How long? Okay, quite quick. So it's quite, so the root mean square error is $726, right? Because the y-axis is in terms of dollars. So anyway, that's all that is. So you guys must see this. I'm just curious. You guys must see this kind of non-distributed, random forest, whatever thing. Which course do you see this in usually?
This machine learning.
Oh yeah. Like Martin Schoen usually teaches.
Yeah, Schoen and Atlantis.
Okay, good. Yeah, so.
Or any machine learning course.
Huh?
Any machine learning course, basically the API will be different based on the
Yeah.
Should be the same.
Yeah, exactly. So so then this one is okay, let's just do linear regression. We're just doing exactly the same thing, except using linear regression, and you see linear regression is worse than the decision tree. Right? So decision trees. So now the question is, can we beat these guys using neural networks, for example, and for this problem? So before we go any further, maybe let me try to introduce you to Keras. So Keras is a high-level application programmer interface for neural networks and deep learning. So the emphasis here is, of course, being able to go from an idea to result with the least possible delay, right? This is what your boss is going to do, right, in industry. So what is nice about Keras is it's actually maintained by Francois Chollet, who's a researcher at Google. It provides high-level APIs, pluggable backends for not just TensorFlow, but Theano, CNTK, MXNet, and all these other things in the bazaar of deep learners. So, which is great because you can stay at one high level and change, the thing underneath, right? Which is great. It has both CPU and graphical processing unit support. And then it's recently officially endorsed high-level wrapper for TensorFlow. Because if you just go and do a Google search, wrappers for TensorFlow, there's a lot, right? But Google, for some reason, and then officially recognizes this, and version ships with TensorFlow. Now we have other niceties like model persistence, because you remember you may work really hard and build a model that you like, your boss likes, then you can persist it. Just write somewhere and come back to it. Okay, and it interoperates with various framework, including Spark deep learning pipelines. So this is actually, deep learning in native Spark. Yeah. Anyway, so
And it's available for hardware.
okay, Russ.
Yeah, so
Okay.
they recently published the package on ground.
Okay, that's good. Yeah, so I'm looking forward to some sugar. What do you guys think? Okay.